and welcome to my classroom. Today we're going to be talking about stoichiometry. Now we hear this big fancy word used a lot by chemists and in chemistry courses. Stoichiometry is just an easy way to think about how do we determine how much of something we need or how much something is going to be produced. And of course we're going to start these problems off again with some Oreos. So let's take a look. So in front of me here, I have a breakdown of an Oreo, just like we had in that other video, of 2 chocolate wafers plus a filling yields an Oreo. And I wrote this little handy dandy little relationship down because we wanted to use it to do some prediction. Now, this time we're going to take it a whole step further. Now, in order to do that, I want to go ahead and convert this to a chemical reaction, a fake one, of course, because there's no chemical reaction occurring, but to help us illustrate a point. So let's say that I create this fictional reaction here of CW, meaning a chocolate wafer, plus 1 filling yields CW2F. That's an Oreo, 2 chocolate wafers and a filling. Now, of course, I've balanced it already using the coefficient of 2. And that's important because we need to be able to use it to ask some questions and perform some stoichiometric calculations. So let's ask our first question. Our first question is going to be, well, how many Oreos can you make with 6 CWs? So in this case, CW is the chocolate wafer. Now, we might automatically in our heads go, okay, well, 1 Oreo has 2 chocolate wafers, or requires 2 chocolate wafers. And I know that there are 3 sets of 2 in the number 6. So that means I can make a total of 3 Oreos. Awesome. You can do that in regular chemical equations too as well, but I want to show you the steps to get that answer because in more complicated ones, it might not happen in your head just like that. So in terms of the steps, it looks something like this. So I have 6 CWs times 1 CW2F over 2 CW. And you can see that that's because what I want is an Oreo, 2 chocolate wafers. And so 1 Oreo has 2 chocolate wafers. And if I do the math, that's 6 divided by 2, and I get that there are 3 Oreos. Perfect. Okay. Now, I want to point out something here. These 1 and 2, where did I get them from? Well, if I look conveniently up here on this chemical reaction I've created, they are the coefficients. The coefficient in front of an Oreo is imaginarily 1, and the coefficient in front of CW is 2. These are molar ratio quantities, and the coefficients play a role in the chemical reactions, which we'll keep touching on here in a minute. But let's look at another example. So let's ask another question. How many wafers would you need? So stoichiometry is not about just asking how much things you're going to produce. It's also about how many things you might need. So in this case, I'm asking how many wafers I need to make 2.5 Oreos. Now, in reality, we know that 2.5 Oreos is quite pointless. Well, unless maybe we want an Oreo with only 1 cookie or wafer. And that's not necessarily correct, but in chemistry, that's definitely going to happen. And you also might not be able to do that directly in your head. That's okay. So if we look at the math, we set up train tracks just like we did before. We can see that we have 2.5 Oreos. What I want is chocolate wafers, CW. What I have is Oreos. Again, I use the coefficients, 2 CWs over 1 Oreo. And I would get then that I need 5 chocolate wafers, which relatively makes sense because if I want 3 Oreos, that means I would need 6 chocolate wafers, and I need 1 less for that, for the half. Awesome. That's how we do stoichiometry. That's all it is. It's just asking questions about, well, how much do we need or how much are we going to make? And using the coefficients in the chemical reaction to figure that out. Let's look at a real life example though. So let's get rid of our Oreos for a second. Shift them over here. And let's look at a common reaction that produces table salt. So in this case, I'm reacting sodium metal with chlorine gas to produce sodium chloride, table salt. Now, quickly, there should be red flags flaring in your brain right now because there is something wrong with that chemical reaction. It is violating the law of conservation of mass, meaning it's not balanced. So I need to balance it. And in order to do that, I need to use whole number coefficients. So I see that I have 2 chlorines, 1 chlorine. Well, I can put a 2 in front of that NaCl and quickly fix that. So I'm going to kind of slightly put it like right here so it doesn't block the space. 2 NaCl. And then that makes now there are 2 sodiums on the right hand side, but now there's only 1 on the left hand side. So I'm going to put a 2 in front of sodium as well. Let me see if I can switch these 2 so that it doesn't cover up the actual reaction so that we can see them together. Ish. We'll just pretend that that arrow is there. It's been erased. Oh well. So that means that 2 sodiums plus chlorines, imaginary arrow, yields 2 sodium chlorides. Great, now we've got a balanced chemical equation. Now, stoichiometry is all about asking questions. So let's ask a question. Let's say, well, how many moles of NaCl can you produce with 2 moles of sodium? Well, all I need to do is set up a train track. Now, this question is asking about a moles to a moles. So if I look at the train tracks, I'm going to go ahead and show you. That means that I have 2 moles of sodium. Okay, great, I understand that. I now know dimensional analysis by heart. It's multiplied by what I want over what I have. Well, what I want in the problem is moles of NaCl. What I have is moles of sodium. Now, all I need is some relationship between the two. And a lot of students go, okay, well, what do I use? Do I need to use molar mass? Do I need to calculate something? All the answers are provided you in the handy-dandy chemical reaction. These coefficients are molar quantities. So in terms of moles of NaCl, well, I know that 2 moles of NaCl yields 2 moles of sodium. Or vice versa, 2 moles of sodium is required to produce 2 moles of NaCl. That's what the coefficients mean. So you've been balancing chemical reactions, but you maybe didn't realize what these actual coefficients mean. They do also still mean the same thing of when you're balancing that 2 sodium atoms react with 1 chlorine molecule to produce 2 formula units of NaCl. That's totally the same as well, but they also mean moles. And you can probably figure out why. Now, so that means I just need to plug in my numbers here. So it would be 2-ish. Sorry, I cut my 2's way too big today. 2 over 2. So it would be 2 moles of sodium, 2 moles of NaCl coefficient, 2 moles of Na coefficient. And then I would get that the answer is, well, 2 times 2 over 2, which is just 2. So that means that they're in equal quantities. So how many ever moles of Na I have, that's how many moles of NaCl I'll have. Perfect. That's all stoichiometry is, converting between each of the units. Now let's ask another question, but let's try a production question. Let's say I wanted to ask, well, how many moles of chlorine would you need to produce 2.3 moles of sodium chloride? This is a very common question because as a chemist, I'm thinking, okay, I want to make some table salt. Well, how do I know how much I need? Well, just like a recipe tells you, I have to convert and figure it out. So if I set up my train tracks, it's going to look like this. 2.3 moles of NaCl. What I want, moles Cl2 over moles of NaCl. Again, I'm using the coefficients as my numerical relationship. 1 mole of chlorine, 1, is equal to 2 moles of NaCl. 2 moles of NaCl. So every mole of Cl2 I have produces 2 moles of NaCl. And that makes sense because every mole of Cl2 has 2 chlorine atoms, where NaCl only needs 1. So that should in theory make some sense. So that means it's 2.3 times 1 divided by 2, which is 1.15 moles of chlorine. Awesome. That's all stoichiometry is, continuing to ask questions. Now, these questions are all about moles. Well, we kind of started asking about Oreos, but now we've gotten to moles. It can go so much further because we know that moles can be converted to several different quantities. We can convert from moles to molecules to atoms, whichever we would like. And we can do the same thing by tacking that onto these simple stoichiometry problems. So if we think about every stoichiometry problem, it's all about following the same path. Well, I might be given a mass of something, a mass of a sample A, and that molar mass of A connects it to the mole, which we know this, right? We know that mass is related to a mole by molar mass. We know this, we've got this. We can say the same thing though, in terms of stoichiometry, is the relationship between a mole of one thing and the mole of another. This is what we refer to as the molar ratio. That's those stoichiometric coefficients. So there's 2 moles of sodium for every 2 moles of sodium chloride. That is the molar ratio. That's what we use in stoichiometry. And of course, we could go from moles of B to mass of B by using molar mass. Now, this trait or these connection pieces, so mass to A to mole to A, mole to A, mole to B, mole to B to mass to B, they can also be further converted. Because remember that mole, I could convert it to molecules, representative particles, or I convert it to atoms. Same thing for this mole. So I can add all those together to create the graphic that you'll see in your course notes to be able to convert between any of them. Let's look at a few examples though. So we've done moles. Let's try mass. So let's ask another question. Same equation. How many grams of NaCl can you produce with 3.27 grams of sodium? Now, first common misconception that happens all the time, students will say, well, okay, Mr. Gamp, 2 moles of Na yields 2 moles of NaCl. So that means that 2 grams of Na produces 2 grams of NaCl. Wrong. Wrong. They are not the same mass, so we cannot make that assumption. So a lot of times students will say, well, it's just 3.27 grams of NaCl. Not true. Not true. We cannot make that assumption. These are only molar quantities. Only molar quantities, not mass. We have to convert it to moles before we can compare it. So in order to do that, we start with 3.27 grams of sodium. To convert it to moles, first step, we need to multiply by the molar mass. So in this case, the molar mass would be 1 mole of Na over the molar mass of Na, 22.990. The second piece that we use is that molar ratio, which is part of the stoichiometric relationship. That's using the balance coefficients from the chemical reaction. So 2 moles of NaCl, 2 moles of NaCl, 2 moles of Na. Perfect. Now, the question asked for grams of NaCl. If I stopped right here, I would get moles of NaCl, which could have been a valid question as well. But I asked for grams, so I need to take one more step. So I need to use the molar mass of NaCl, moles of NaCl, and I multiply by 58.44, and I get that the answer is 8.31225 grams of NaCl. Again, red flags should be flaring right now because you know this. That is not right because my answer is not that significant. Clearly, I have an amazing balance that measures to the several thousandths place. That's not correct. I need to follow the same accuracy that was provided in the problem. So the problem says 3.27 grams. So that is 3 significant figures. I've done nothing but multiplication and division, which means that my answer should also have 3 significant figures. So I should put 8.31 grams of sodium chloride. You need to follow this every time you complete any of the calculations moving forward, because if you put this answer into blend, you will get it wrong. You have to put the correct number of significant figures. So make sure that you're paying attention to that. That's how you go from grams to grams. Again, same thing. We're just adding extra steps. That's all it is, little additional steps. And we can add more steps. So let's ask another question. Same equation, but now we're going to ask about molecules. So what if I said, well, sorry, my question got stuck. How many molecules of Cl2 would you need to produce 23.9 grams of NaCl? Phew. I know, right? How the heck am I going to answer that question? Well, I have to break it into steps. Well, I was given grams. You already know that you need moles in order to use the coefficients. So I'm going to have to convert from grams to moles. And the last problem I converted from moles to grams at the end of the problem. This one I'm going to need to convert to molecules instead. So let's look at the train tracks. So I started with 23.9 grams of NaCl. I now want to get to moles. So in order to get to moles, I need to multiply by the molar, or divide by the molar mass, which would be 1 mole of NaCl over 58.44 grams of NaCl. Perfect. Now I'm in moles of NaCl. This is why it's very important to write down the compound that's being related, because a lot of students, what they'll do is they'll write 23.9 grams, and then they'll write 1 mole over 58.4 grams, and then they'll get to this problem, and then they'll be like, what compound was I in? So please write those down. That really helps us as teachers too to follow along your steps of what you're actually doing. So next is that molar ratio using the balanced chemical equation. So 1 mole of Cl2, 1, over 2 moles of NaCl. Perfect. Now I'm in moles. Now the last time we went to grams, this time we want to go to molecules. Well, we know that the connecting piece between moles and molecules is Avogadro's number, which means I need to use Avogadro's number. This is the number of molecules in 1 mole. If I follow my math, okay, perfect. I get my answer in molecules. So if I do this math, I get that it's 1.231 times 10 to the 23rd molecules of chlorine. Again, red flags. That's too significant. 1, 2, 3 sig figs, so my answer should have 3. So it should be 1.23 times 10 to the 23rd molecules of chlorine. Now, I want to pause here for a quick second. Every one of these problems I'm working out using the train track method. You do not have to use the train track method. If you want to do individual calculations until you get to the answer, perfect. If you want to use ratios, perfect. If you want to use complex ratio problems, also fine. There are several ways to answer these problems. And don't think that we're going to hinder you based on the process that you follow. As long as you write down your process, that's what we need, because we need to be able to see that you can think through the steps in order to get the answer. Perfect. Now we've went to mass. We went from mole to mole. Awesome. That is stoichiometric calculations. Every time it's asking a question, how much do I need or how much do I want? Great work, Velociraptors. Now you've done your first set of stoichiometric calculations. You understand what a molar ratio is when I'm comparing two different reactants or products and products or reactants in a chemical reaction. That's where those coefficients come into play. We now know how to go from moles to mass to molecules, or any combination of those. And we can use them all the same steps and same methods when we do our stoichiometric calculations. So good luck practicing. If you need any support or help, please reach out to your instructors. Thanks for tuning in.